Have you ever really looked at the graceful arc of a basketball shot or the curve of a satellite dish? That beautiful shape is a parabola. Well, today, we're going to crack its secret code. We're going to learn the simple rules that let us take one basic parabola and stretch it, flip it, and move it anywhere we want on a graph.
So let's dive right in. The key here is to stop thinking about these equations as just, abstract math problems. Think of them as blueprints, visual instructions. Every single number and symbol is a command telling us how to draw, move, and reshape our curve. It's actually a pretty creative process, and by the end of this, you'll be able to read that blueprint in a single glance.
Here's our game plan. First, we'll meet the original, the parent parabola. Then, we'll learn how to move it up, down, and stretch it out. After that, we'll tackle the tricky sideways slide. Then we'll combine it all into one master blueprint. And finally, we'll see why this whole thing is such a powerful and important idea.
Okay, first things first. We need a starting point, right? Every single parabola you'll ever see is just a modified version of one simple, foundational curve. So, let's meet the parent.
And this is it. F of x equals x squared. This is the parent function. You can think of it as the original template from which all other parabolas are made. The most important things to notice are its two key features. Its vertex, that's the bottom point of the curve, is sitting right at the origin, at 0, 0. And it opens up, kind of like a bowl.
The relationship here is as simple as it gets. You pop in a 1 for x, you square it, you get 1 for y. You pop in a 2, you square it, you get 4. And check out that perfect symmetry. A -1 also gives you 1, and a -2 also gives you 4. This symmetry around the y-axis is absolutely fundamental. Just try to burn these points into your brain. They're going to be our anchor for everything that comes next.
Okay, we've got our parent parabola. Now, let's start messing with it. We're going to look at changes that happen outside the function. These are the ones that affect the graph vertically. And the great news is they work exactly the way you'd think they would.
So what happens if we just take our basic x squared and tack on a +3 at the end? Well, the entire graph just slides straight up by 3 units. Every single point on that curve moves up by 3. It's that simple. The shape doesn't change one bit, only its position.
And, as you've probably already guessed, subtracting a number does the exact opposite. X squared minus 3, that just shifts our whole parabola straight down by 3 units. So there you have it. Adding or subtracting a number on the outside is our up and down control knob.
Okay, but what if we multiply? Let's take a look at 2x squared. We call this a vertical stretch. For any x value you pick, the y value is now twice as high as it was before. It's like we grabbed the two arms of the parabola and just pulled them upwards, which makes the whole thing look narrower or skinnier.
And for our last vertical trick, what if we multiply by a negative number, like -1? Bam! The entire parabola just flips upside down. It reflects perfectly across the x-axis. Every y value that was positive is now negative. This is how we get all those downward opening parabolas.
So we've totally mastered the vertical moves, right? Those all happen outside the squared part of the function. Now we're going to go inside the parentheses. This is what controls the horizontal or sideways shift. And I'm going to give you a heads up. This one feels a little counterintuitive at first, but I promise there's a perfect logic behind it.
Okay, let's just think for a second. We just saw that adding a number on the outside moved the graph up. So it seems totally logical that adding a 3 inside the parentheses to get x plus 3 squared should move the graph to the right, shouldn't it?
Well, here's the why. This is the key. To get a y value of 0 in our parent function, x just has to be 0, right? Because 0 squared is 0. But now look at our new function, x plus 3 squared. To get that same output of 0, what does x have to be now to make the part inside the parentheses 0? It has to be -3. To get the same result, our input, x, has to compensate. It needs to be 3 units smaller than before.
So, this is the big rule for horizontal shifts. They do the exact opposite of what the sign makes you think. So x minus 3 squared actually moves the graph 3 units to the right in the positive direction, and x plus 3 squared moves it 3 units to the left in the negative direction. It's weird at first, but once you get that logic of compensation, it totally clicks.
Okay, we have all the pieces. We know how to move the parabola up, down, left, and right. We can stretch it, and we can flip it over. So now it's time to combine everything into one single, powerful master equation.
This right here, this is called vertex form, and it is the master blueprint. The A value out front, that's our stretch and reflection control. The K on the end is our simple vertical shift, and that H on the inside is our horizontal shift, but remember, it's the opposite sign. And the best part? The two numbers, H, K, literally just give you the coordinates of the new vertex.
Let's watch how we can build a really complex-looking graph just by reading the blueprint. We always start with our basic parent, x squared. Then, the x minus 3 tells us shift it right 3 units. Okay, the 2 out front says stretch it vertically. Done. The negative sign in front of the 2 says flip it upside down. And finally, that plus 5 on the end tells us lift the whole thing up by 5 units. See, each piece of the equation is just one specific move.
And there it is, the final graph. Now look back at our equation, minus 2 times x minus 3 squared plus 5. According to our blueprint, the vertex h, k should be at 3, 5. And that's exactly where it ended up. The code works. It's perfect every time.
So, okay, we can move a parabola around. Big deal, right? But this is so much more important than just getting an answer on a math test. It's really about changing how you see the connection between the symbols on a page and the shapes of the world around us.
What you've really done today is unlock a new kind of literacy. You can now look at an equation in vertex form and instantly see a picture of it in your head. You've learned the absolutely crucial difference between making changes inside a function, which affects things horizontally, and making changes outside, which affects things vertically. This is a core concept that applies to pretty much all functions, not just parabolas. You've learned to see math as a language that describes shapes.
Think about it. Every type of function out there, straight lines, circles, wavy sine curves, they all have a parent function and they all follow these same kinds of transformation rules. We've just cracked the family code for quadratics, so the real question is, what other visual secrets are hiding inside all those other function families just waiting for us to come and decode them?